So the Burj Azizi is being built in Dubai. It's going to be next to the tallest building in the world, the Burj Khalifa. You can see in this rendering in the background, you can see the Burj Khalifa. This is on Sheikh Zayed Road, looking towards Abu Dhabi. Here's some of the images of the skyscraper. These are obviously looking towards the towards the Gulf on the first two on the left, and then from the backside looking towards the Sheikh Zayed Road and Burj Khalifa. The project. These are different renderings. This is Sheikh Zayed in the front, in the Gulf to the rear. You have the Emirates Towers and the Museum of the Future to the left-hand side. From the Gulf, looking towards the Burj Azizi, from the metro, and from the Dubai Museum of the Future. Some nighttime photos. And then here you can see the comparison from the Burj Azizi to the Burj Khalifa. There's also a large parking garage that also houses a banquet hall, beach club, and many other that has cooling towers. All the utilities are incoming here, but it's another large component of the project. So some of the statistics. So Burj Azizi is a mixed-use tower. It's primarily residential and hospitality. It's 144 stories. As you can see here in the what we call the stacking diagram on the left-hand side, at the very base, we have the green, which is a retail base. It's 8 stories of retail. Above that, we have MEP plant floors, main kitchen for the hospitality, the area for the banquet hall. And then you can see in the blue above that are the residential zones. So we have 3 different types of residential. We have holiday homes, we have freehold apartments, and we have penthouses in the light blue. And that takes you pretty much up to the level 96. And then from level 96 above in the red, you have hospitality. So you have amenity floors at the base. You have the hospitality lower suites and upper suites. And then above that, you have nightclub and what we call the adrenaline zone, which is really a series of levels for observation deck and different events at the very top of the building. The GFA is 237,000 square meters. The built-up area just for the tower does not include the parking garage is 320,000 square meters. So getting to the structure, the structural system is a tube-in-tube system. So here you can see the different views of the structure. So basically, it's an exterior cage with an interior tube, the core. So you can see from here, the plan to the lower left shows the core. This is a very tight site. This is only the footprint of the building is 57 meters by 53 meters. So the slenderness ratio is a 12.5 to 1 slenderness ratio. Extremely tight site. So we have a core, obviously on the interior, and then we have an outer cage of concrete columns and beams. And then at the MEP plant floors, we have outriggers that connect the tube, each tube, the exterior tube to the interior tube. The foundation system, so here you can see on the right-hand side is the exterior frame of the columns and the beams, the exterior cage. And then on the left-hand image, you can see the foundation system. It has 2 basements, and it has a 5-meter deep raft, and it sets on breadths. So the breadths, if they're not familiar with breadths, they're a rectangular pile, so to speak. They're very accurate in terms of we had to go down very deep. These breadths average around 70 meters deep. Piles go out of tolerance at that depth. So you're able to control the accuracy, the tolerances with the breadth much more accurately. Plus, they give you much more stability and capacity in terms of the loads that we're dealing with. We have roughly, so you can see here, a section through the breadths with the perimeter coming down around 50 meters, and then you have the interior at the core coming down 70 meters. And then here you can see a plan of the breadths. The tower is asymmetrical in its loading. So you can see on the left-hand side that the breadths are lighter. You can see they become denser at the bottom right. And obviously you can see at the core, they're the densest. Now, this is the second. These breadths were already put in place for another project that did not go through. And so Azizi took over the site. They bought the development rights and took over the site. So they inherited the breadths. And then for this, we had to add roughly 12 breadths. The original tower that was scheduled for here was 528 meters. This is 725 meters. So added 200 meters. And then here's some more structural drawings that basically show this is the ground floor. So this is just basically showing the column, the perimeter cage, and the core. We have 41 elevators for the project. Most of them you can see primarily they all occur in the core. There are some perimeter elevators that occur at the periphery of the project. And then these are plans of where the outriggers connect to from the core to the exterior column cage. This is the first level at level 9. We only have them running in the north-south direction. And then as we go up, they connect in both north, south, and east-west. And as you go up, the tower diminishes, the footprint of the tower diminishes in size. And you can see it's also asymmetric. There was a lot of shaping that took place for wind tunnel testing. One of the big issues with the Burj Azizi, one thing, it did not face an issue in terms of acceleration. It faces an issue in terms of drift. So controlling drift, Dubai municipality limits drift to L over 400. That includes interstory drift. So that was an extremely restrictive criteria to achieve. We have achieved it, but it was very difficult. We've had to go through several iterations in terms of strengthening the columns, making them more rigid. Obviously, that means making them larger. We have a lot of different composite sections. We have concrete filled tubes. We have a variety of column types for the project. We do not have a consistent floor to floor. One reason is for MEP floors, we have public assembly areas, restaurants that require higher floor to floor. We have amenity floors, higher floor to floor. So the basic, like the residential, basically 3.725 floor to floor to 4.1. The penthouses go up to 6 meters floor to floor. And then when we get to hospitality, they're basically 5.1 floor to floor. At the very top, we have a crown. The crown that extends, that cantilevers above what we call the glass box or the glass spine, is actually 70 meters in height. Actually, we're working with D. Simone in New York for this. And then this is adrenaline zone. There's a series of activities up in the adrenaline zone, rock climbing walls, restaurants with floating spheres. See, these are some of the drawings. So you can see the culmination at the very top, how the concrete frame stops, and the blue that represents what we call the crown and the steel portion, and the cantilever. And these are the setting out drawings, the geometric setting out drawings for the crown. And then here's the wind. So the wind tunnel testing was actually done in India. We're working with RWDI. So you can see here the height of the tower in relationship to the adjacent to the context towers. The towers surrounding the tower, Burj Azizi, are 50 stories in height. Again, our top floor is 144 stories. Now here, what's interesting, this really starts at the top of the project that shows the acceleration. And we did not have to add a damper for this building. We did not have to add a supplementary damper. We did a lot of shaping of the tower in desktop studies and preliminary wind tunnel studies. So we had a force balance test. We've had a pressure integration test, cladding tests. We're now about to start an aeroelastic test. But you can see here, the graph on the right is for residential. And you can see, actually, I want to go back. This is actually the lower portion of the tower. So the acceleration is far under, you can see the green is what we need to be able to, 15 milligis, 15 to 18 milligis to be satisfactory for residential. And we're far below that. These are as you go up in the tower. So the one on the left-hand side is when you get to the adrenaline zone. So the acceleration up there, we're still within the office realm. We're assuming a 1.5% self-damping from the concrete. But it was interesting that we did not need a supplementary damper for this project. Here, I'll just very quickly touch on the skin. We did a lot of work on the skin. The skin performs in terms of it limits the amount of solar radiation entering the building. We actually developed vertical fins that that provides self-shading. So we worked with Nia Pauli in Kuala Lumpur to do solar radiation mapping to understand the baseline for the tower, where we were getting the most amount of solar radiation. We went through a series of studies. Obviously, we analyzed it throughout different times of the year and at different times of the day. And then we looked at what if we put a vertical fin on it? How, if we put a vertical fin on it, would that be able to help us in terms of self-shading and the performance of the skin? So basically, we went through a lot of different iterations. You can see the upper left-hand corner is the baseline, no fins, no articulation. And we went through different depth of fin, frequency of fin in terms of getting to a sweet spot. And we arrived at a fin that occurs basically every 4.5 meters on center with an 800 millimeter projection. And then what this enabled us to do was relax the solar heat gain coefficient. So by Dubai municipality, we require a 0.24 for the solar heat gain coefficient. We were able to have a more transparent glass with a relaxed solar heat gain coefficient, but give us the performance that we needed from a 0.24. And then these are some of the models, the computer models of these fins, the curtain wall development. It integrates all the BMU as well into it. You can see here a rendering of the fin on the right-hand side actually has a reflective, it's a chrome frit, and then this is a mock-up that's done by Future Glass of the same fin, but you can see the frit, the chrome frit, to maintain the continuity of the reflection of the glass. And then these are the savings. So by adding these fins, we're able actually to save 1.21 megawatts of capacity, cooling load capacity, by adding those glass fins. But I think I'm running out of time. So there's other aspects of the tower. There's the retail base. It's a double skin. We used a double skin to ventilate the facade. And we did CFD studies with Neapoli. We have these vents that are integrated into the facade that allow air to pass through. And this is the very base of the tower, the first 8 stories of the tower. And then I would just quickly get to, it's under construction now. These are current construction photos. This is the parking garage. They're starting with the parking garage first. The foundations are already in. The parking garage itself is 16 stories. We have automated parking for the parking garage. So it's a 25-meter deep basement. So this is the beginning of excavation for the automated parking. On the right-hand side, you can see the tower, the excavation for the tower. You can see here the breadths are all in place. This is the tower excavation. And with that, I thank you for letting me present the Burj Azizi.